I'm Brian von Herzen from the Climate Foundation. I'm going to talk with you today about biochar in particular, but especially security when it comes to sanitation, when it comes to food security, and when it comes to water security going forward. I think that's really important. The previous talk was a great introduction to the process of carbonization, and whereas the hydrothermal carbonization takes us to lignite, biochar takes us to anthracite or graphene. So we take the process further. We go beyond the standard C6H12O6, and we go to carbon and water. So it takes the process further. And the question is, how can we leverage this process, which is somewhat natural, to actually make a big difference in sanitation as well as in agriculture? So what is biochar? Biochar is a prehistorically proven anthropogenic source of soil fertility. The terracretan soils of the Amazon basin have proven to be some of the most productive soils in all of South America. And what's unique about them is that they seem to have been created by man some thousands of years ago, which is a great historic precedent, because it turned out it wasn't even in the fields of Brazil where the biochar, or I should say the terracretan soils, were made. But originally it was actually out the back kitchen window, and it was a pure accident. The accident was that they threw out the charcoal, they threw out the fish scraps and all sorts of other refuse, including fecal solids, I'm sure. And they noticed after a few decades, or perhaps 100 years, that the weeds were growing better out the kitchen window than they were in the fields. And they wondered, well, what's going on here? And there's some debate as to whether it's intentional after 100 years that they started actually learning and deploying the biochar from that basis and developing terracretan soils further. But at least to begin with, there's good evidence anthropologically that the biochar was accidental. And yet, we have to this day some of the most productive soils in all of South America. And you can still pick up pieces of biochar in these terracretan soils, and you can see the texture of the wood that made the biochar. So we have incredible permanence, a demonstration where man sequestered carbon a millennium ago, and it's still there in the soils today. And to me, that's very inspiring, because this is a rare indication of man's carbon sequestration potential in soils. And the potential is truly enormous, potentially gigatons per year, if applied inefficiently across agriculture and perhaps sanitation on a global basis. So that's some of the process and the promise that we have. In fact, to this day, these terracretan soils are mined, and there's some evidence that they actually grow over time, because it turns out these soils are alive. They're not just the carbon in and of themselves, but also the mycorrhizal fungus and the microbes associated with them, which I'll show you more of in a moment. Physically and chemically, what is the biochar? Well, the brick on the left shows a temperature range of 400 Celsius up to perhaps 800 and 1,000 or even higher, and what happens to the carbon structure as the temperatures rise. It starts out very disordered, which promotes a high surface area and even a high cation exchange capacity, which could maximize at perhaps 600 or 700 degrees Celsius. But as you can see from this diagram, after 800 Celsius and higher, the carbon actually becomes more ordered, and you start getting an anthracite coal, if you will, a very ordered layer. So it's this medium range of temperature around 600 or 700 Celsius where you can actually maximize the surface area and maximize the cation exchange capacity, which then ends up being very beneficial in agricultural applications. Now, it's all about the hydrogen, the carbon, the nitrogen, and the oxygen. So we had our approximate ratio of C1H2O1, and with heat, we actually get the carbonization either incrementally or completely, and through pyrolysis, we get a combination of partial combustion products, hydrogen, and carbon as well. The carbon is in solid form as biochar. The H2 and the CO are in the form of syngas, and that syngas can be successfully combusted to complete combustion, and when it is, it provides essential energy for propelling the entire operation. So it ends up being a great way to both create the energy syngas needed to fuel the process, as well as the carbon biochar itself. The best model that we have for this are small disordered sheets of graphene in the temperature ranges of interest. And you can see how this works. If these sheets are disordered, they have a very high number of dangling bonds, providing the high cation exchange capacity, and the small sheets of graphene have an enormous surface area, especially when separated by just a few nanometers per layer. So why is biochar important? Well, not only does it potentially address the treatment and sanitation of human solid waste, but in agricultural applications, it reduces the fertilizer requirements because of the high surface area. Fundamentally, what biochar is doing is rendering soluble nitrate fertilizer insoluble. And when you make it insoluble, then when you apply fertilizer to the land, it does not wash into the groundwater after the first rains, after the first monsoon. But instead, the nitrate fertilizer remains near the roots of the plants through the rains year after year. And the net result is an accumulation and a benefit that takes place over years and decades. And that dramatically changes the equation for the productivity of our agriculture. At the same time, biochar acts like a sponge. It actually absorbs water. It increases the water holding capacity of the soils. And as a result, you are able to, these plants can survive and thrive in an era of increased drought and reduced availability of fertilizer. So this fundamentally increases the arability of the land and enables extensive agriculture, where we're extending our agriculture over larger regions. So it ends up multiplying, and this multiplying effect ends up being significant. What do the soils look like? On the left, there's a conventional tropical soil. In the middle, a biochar, a terrapretin soil, which means dark earth in Portuguese. And you can see it on the microscopic scale, a very high surface area and structure. In the lower right, the mycorrhizal fungi actually take up habitat inside of the biochar structure. While the biochar is biologically unavailable, it provides a habitat for beneficial microbes, and that is an essential aspect of increasing the mass of this biochar soils over time, all by themselves. Some of the anecdotal results include that biochar with NPK fertilizer produces better results than NPK fertilizer alone, particularly in the proper environment. And the key question is, can we make biochar from human solid waste? Well, it's challenging because human solid waste has a high moisture content, and fundamentally we're dealing with a moisture problem. Now, the challenge and the opportunity is, how can we manage the moisture problem? And fundamentally, we take an approach that is relatively simple, but the idea is, if we have a moisture problem, don't add water or urine to a moisture problem. And so fundamentally, the urine diverting toilet is the approach that we've taken for this, because we feel as though it's essential to providing this. On the right-hand side is the EnviroSan urine diverting toilet that we have worked with and look forward to incorporating in our future designs. And on the left side is the SanerGy's squat plate design for a urine diverting toilet that's implemented in dozens of locations in Nairobi. And that's an essential aspect to this overall process, is to be able to actually divert the urine. Here's a further picture of SanerGy's infrastructure sanitation unit. At a cost of less than $200 per unit, it's a very effective way of doing the collection. And one of the key aspects of this, as we see it, is building the infrastructure and the business model for making this happen. And so we've partnered with SanerGy, and they have pioneered not only the collection with these urine diverting sanitation units, but then the coalescence, the aggregation of and the supply chain management. We have regional processing facilities. Shown in the center are the regional processing facilities, which could be some hundreds of meters from the actual sanitation units. And they've actually created a successful business infrastructure for doing this collection on a regular basis. Our biochar reactor then helps SanerGy's infrastructure in being able to process and convert the human solid waste into biochar, which can then be combined with conventional organic fertilizers and distributed to farms throughout Kenya, in this case, for use in agriculture. So SanerGy has pioneered that vertical pipeline. The biochar reactor that we are developing is really a solution to the sanitation of that human solid waste, and it's a direct approach to doing it. Now, there's an important thing to bring out here, and that is that when it comes to investing in our soils, I think there's a very important concept that Professor Johannes Memmen from Cornell has brought forward, and that is the notion of soil capital. And what I mean by soil capital is that we're actually increasing the content of carbon in our soils when we add biochar. And this is a very significant benefit because not only are we addressing the human solid waste issue, but we're also actually increasing the carbon level in the soils, which ultimately provides dividends over a period of 50 years. This chart shows that by far the greatest benefit and the greatest effect is over a time scale of 50 years. It is the increased maize production that's produced in this particular example over a 50-year time period that actually produces the greater net present value of biochar over that time period. There are benefits in carbon sequestration, greenhouse gas reduction, time saved, and one-year crop effects, but by far the biggest effects are actually measured over decades. So we have this notion of financial capital, and we have a notion of human capital, but this is extending this further to environmental capital in general, and to soil capital in particular. And I think investing in our soils is a key example. So I did a little back of the envelope calculation that, you think of your bank account, you put money in your bank and you save it there, which is just fine. Except if you have 3% inflation relative to the interest rate, then over a period of 100 years, that bank account goes to about 0.1 or 0.2 of its normal value. That's the lower curve that I've drawn here over a century. Conversely, if you invest in soil capital, if you put biochar into your soil, and it's able to accrete with the benefit of mycorrhizal fungus at a mere 1% per year, you can see a tripling of the carbon in the soil over a century. And that's what we mean by soil capital. It's the opportunity to see an exponential increase in agricultural productivity in comparing a desert to comparing a tropical rainforest or high production region. That's really the opportunity before us. And so, in a real sense, we're talking about black gold, and black gold in this case is biochar. So how do we actually make biochar from human solid waste? Well, some of the key aspects here is energy management, and we have to do it efficiently. So this block diagram shows on the left-hand side human solid waste being input to the system. And this is a system that we built at a small scale since 2011, and are planning to do it at a much larger scale next year. And the plan is to pre-dry on the left and provide a moisture reduction facility there, followed by pyrolysis in the center. And that's where we are actually heating up the solid waste in a low oxygen environment. And in that low oxygen environment, two things occur. The evolution of syngas, which goes into lean burn combustion on the right, and the evolution of carbon in the form of graphene biochar, which is then extracted and provided as a biochar output. Now the lean burn combustion produces that H2 and the CO, it takes the H2 and CO, and it actually converts it into complete combustion with an exothermic capacity that approaches the 17 megajoules per kilogram that Simon had mentioned previously. Through a heat exchanger, we're able to transfer that heat both to the pyrolysis unit to promote the pyrolysis of the input solid waste, while at the same time facilitating the pre-drying operation on the left-hand side. And that is the key to efficiently manage, through a heat exchange process, this overall system. Following the pre-dryer heat exchanger, there's in fact a second one, counterflow heat exchange, that actually heat exchanges with the incoming air, because it turns out the temperature of that incoming air is very critical going into the combustion chamber and determines the overall energetics. The net result is that we have an exhaust system at the end, on the right side, that could be 60 or 70 degrees Celsius, even though our internal combustion temperatures may have exceeded 500 Celsius. As a result, we have a very efficient approach because we're able to effectively manage the thermal losses through counterflow heat exchange. By the way, the biochar not only is great in soils, but it also acts as an excellent activated charcoal filter. So odor management is a key aspect and focus of what we're doing, and we actually have three aspects that this system manages odor. The first is the operation below atmospheric pressure, so that the air leaks in rather than the odors leaking out of our system. Secondly, the lean burn combustion oxidizes odoriferous sulfide compounds, for example, to sulfates, which are far less odoriferous than the sulfides. Thirdly, the biochar activated charcoal filter can actually charge up the biochar while at the same time eliminating any residual odors. The net result is that we have a framework for actually managing odors in our system as we go forward that we believe will enable this system to operate in an urban environment. So what does our biochar reactor look like? Well, at the small scale, and this system is designed for a village scale operation, perhaps 100 people per day. That's the system we were asked to implement initially. We have 3 chambers. It looks like a Russian doll. In the middle is pyrolysis. Outside of that is the lean burn combustion. and outside of that is the heat exchange with the actual incoming air. And the net result is that just as the chicken legs keep the toes of the chicken cool while retaining the heat of the chicken, similarly we're able to keep the center of pyrolysis hot while at the same time warming the incoming air and cooling the exhaust air. And that's the overall architecture of our system. In addition, on the left side, there are two rectangular scrapers that actually scrape biochar off of our turntable architecture. And that turntable architecture is attractive because there's simply a single moving part at the high temperature, and that is a friction bearing on the actual turntable itself. The net result is we're able to deposit the input feedstock, dry it, and pyrolyze it all in the same mechanism, very conveniently, with a minimum of moving parts and a maximum simplicity, which will operate for longer times in the field since it's more reliable. So a bottom-up view of this system is shown here with the lean burn combustion chamber in the bottom with several air holes, the turntable that I mentioned here in the center for doing the actual pyrolysis in this upper pyrolysis chamber, and a square chute for the actual biochar output. And at the top, an output for the exhaust gases and for the incoming air, as well as the input feedstock material. With instrumentation and thermocouples, it looks like so. And then we've added, of course, plenty of insulation, because the insulation is a key aspect of the thermal management, along with some dark black objects, which are in fact biochar that we've produced with that machine, and our demonstration at the Reinvent the Toilet Fair and the Gates Foundation this past August. So the energy budget with a 60% moisture content input looks at about 8 megajoules per kilogram wet, which is corresponding to roughly 20 megajoules per kilogram dry, minus 1.35 megajoules per kilogram for the heat of vaporization. Effects include thermal capacity to warming the water, warming the dry fecal solids, and heating the steam, with the net result that we still have over 5 megajoules per kilogram remaining in order to manage the thermal losses in the overall processing. So there is quite an energetic budget that's available there. And as we increase the moisture fraction approaching 75%, it becomes more of a challenge, and that's where we're going to be using this excess remaining energy. And so as we get to the higher moisture contents, we have to actually stretch our abilities to operate very efficiently, while at the same time enabling this reaction to take place. These are the pictures of reactor nozzles that for the syngas for lean burn combustion. A couple of views of the combustion chamber itself, burning the syngas directly from our simulated material, NASA simulant material. Some time plots of our thermal trajectories over a 51% moisture system and over a 60% moisture system with a half-hour burn, resulting with our feed rates in this case of 3 kilograms per hour, and a view of the demonstration at the US Biochar Initiative conference in July. So this is our overall system setup. Here's some of the results of our biochar produced at a moisture level of approximately 60% this summer, and this is in our small-scale system. Our large-scale system, we hope with further support in 2013 to build a system suitable for thousands of people in urban slums throughout the world. And our first system will be deployed in Nairobi in partnership with SaNRG. And we hope to develop the system as a larger scale operation that enables us to do the pre-drying and the pyrolysis and the biochar generation in an efficient manner in a containerized system that can be transported around the world. And we hope with further support to demonstrate that in a year's time. This timing could not be any better because we are just in time on this technology. And the reason I say that is we're faced with compounding challenges, and that is we're seeing droughts around the world that are forecast to be decadal in scale, both in the United States, in Africa, and in the Far East. We're dealing with increasing droughts. Biochar is severely needed to maintain our food productivity in a world of drought. And that's something that we view as an essential technology going forward. So not only addressing sanitation, but this agricultural aspect. And secondly, our source of petrochemical fertilizers is dwindling. Here in this example in the United States, we have reached peak oil, and the peak oil is decreasing. So if we're going to have to use less fertilizer, we need to use it more efficiently. And biochar is key to doing that. So we view this as a multi-dimensional key to addressing sanitation problems with urban poor in particular, to addressing the need to increase food productivity in the face of increasing droughts and decreasing petrochemical fertilizer availability. All these benefits can accrue from a biochar framework that we hope to build with our partners. Together, we can ensure food productivity and food security in the face of droughts, and ensure sanitation and the availability of access to sanitation globally. And we see that as a key to moving forward together and enabling this kind of solution. Please join me in this work and helping us to achieve this vision of the future. And thank you very much for your attention.